Counterfeiting poses significant risks to public safety and health, with counterfeit goods infiltrating untrusted supply chains through complex distribution channels. Researchers have proposed various anti-counterfeiting solutions, including special inks, laser engravings, and optically variable features. However, these methods add overhead to the verification pipeline and often require specialized techniques, restricting supply chain stakeholders' participation. In contrast, paper-based authentication systems leverage microscopic imperfections in paper surfaces to authenticate products, offering an economical solution. This work aims to systematically unify two separate research areas, creating unclonable identifiers and securing virtual records using distributed ledgers. The authors introduce a generalized paper-based authentication framework, identifying important shortcomings and promising ideas in existing literature. They conduct a stage-wise security analysis, drawing inspiration from signal processing, cryptography, and biometric systems. The supply chain is demarcated into two distinct worlds: the physical world, where the product resides, and the cyber world, which houses records detailing product movements. A holistic understanding of the security of both worlds is essential, as they interact regularly. The authors examine the physical world, discussing extrinsic identifiers such as barcodes, QR codes, and RFID tags, which have severe security shortcomings due to their unencrypted design. They also explore intrinsic identifiers, including special materials with unique visible features, such as bubble tag and fiber tag. The authors highlight the limitations of extrinsic identifiers, motivating a solution that adds minimal overhead to the supply chain, is easy to acquire, and provides adequate authentication performance. They propose using physically-unclonable identifiers, PUFs, of paper surfaces, which offer a secure and robust solution. The paper-based authentication framework is designed to evaluate and categorize existing anti-counterfeiting systems, creating an extensive taxonomy and outlining crucial security vulnerabilities overlooked in the existing literature. Intrinsic identifiers, specifically optical physically unclonable functions, PUFs, are a class of candidates that satisfy the properties of being unclonable and unique. PUFs have been widely used as primitives for cryptographic protocols, such as key distribution. Existing work has largely focused on paper surfaces due to the ease of modeling its interaction with light. The extraction of the inherent randomness of the paper surface has been studied using both physical modeling and visual appearance. The limitations of extrinsic PUFs motivate the consideration of intrinsic PUFs as a scalable alternative. Paper-based anti-counterfeiting solutions are inspired by the economical nature, simplicity of physically modeling interactions with light, and abundance of prior studies. However, the assumption that micro-level intrinsic features extracted from the paper surface are unclonable has not been explicitly justified. The papermaking process is an elaborate process that combines different intricate chemical and mechanical steps. The process can be abstracted into 6 steps, with the largest amount of randomness introduced during the process of forming. Uncontrollable differences arise between different paper sheets at every stage of the pipeline, with the forming process introducing the most randomness. To understand the suitability of paper microstructures as an optical PUF, standard PUF metrics such as robustness and uniqueness are evaluated. The robustness metric measures the stability of the output under different evaluation conditions, while the uniqueness metric measures the discriminative power of the PUF. The evaluation metrics inform a system designer about the feature variations, which shine a light on the feasibility of using a feature for authentication. The use of intrinsic paper PUF identifiers is justified by examining the papermaking process and identifying the key step that introduces randomness into the microscopic texture of a paper surface. The paper microstructures are shown to satisfy standard PUF metrics, making them a suitable candidate for authentication. The paper discusses the properties and security of paper-based physical unclonable functions, PUFs, for anti-counterfeiting systems, identifying 4 key metrics: robustness, uniqueness, uniformity, and ease of evaluation. The authors argue that paper PUF-based systems satisfy these properties, making them suitable for deployment. They also discuss physical attacks on paper PUF-based systems, including denial of service, DOS, attacks that aim to destroy the texture of the paper surface. While such attacks can reduce the robustness of the system, the uniqueness of the paper puff response remains stable. The authors propose a general framework for paper-based authentication systems, which consists of 4 stages: image collection and preprocessing, feature extraction, storing reference data, and decision-making. This framework is illustrated using a norm map-based anti-counterfeiting system. The paper also develops a comprehensive taxonomy of existing anti-counterfeiting methods, categorizing them based on physical and cyber world solutions. The authors evaluate the deployability of these systems based on desirable properties such as non-proprietary design, unclonability, and the use of standard equipment. The paper concludes by highlighting the potential of paper puff-based authentication systems for real-world applications, despite limitations and challenges. The authors emphasize the importance of understanding the security of both the physical and cyber worlds in combating counterfeits. They also present a comprehensive analysis of anti-counterfeiting systems, focusing on paper-based authentication methods, and discuss the limitations of existing systems, highlighting the importance of understanding key threats to each operational stage and providing a set of representative mitigation strategies. The paper discusses various attacks on a product authentication system, focusing on 4 stages: feature extraction, feature comparison, reference database, and decision-making system. It highlights potential vulnerabilities and proposes mitigation strategies for each stage. In the feature extraction stage, the paper suggests using invisible feature forensics modules to detect synthetic features and implementing lockout mechanisms to limit the number of queries an adversary can make. For the feature comparison stage, it recommends using blockchains or blockchain database hybrids for securing the database and leveraging concepts from biometrics and security practices such as salting, revocable non-invertible hashing, and biometric crypto systems to protect against leaked templates. In the decision-making system stage, the paper addresses hill climbing attacks by suggesting the use of information leakage-resistant distance metrics or limiting the number of queries through lockout mechanisms. It also proposes using Pearson correlation as a similarity metric instead of LP norms, which have been shown to leak information about raw templates. Finally, the paper discusses attacks on interfaces between modules, particularly replay attacks, and suggests using strong cryptographic protocols like TLS and timestamping to mitigate these attacks. The paper concludes by consolidating its attack mitigation strategies into best practices for supply chains and examining real-world application examples in different scales, focusing on authentication systems based on norm maps due to their numerous advantages. Here is a combined summary of pages 13-16 of the research paper. The authors discuss the application of hybrid models in medium-scale supply chains, such as the semiconductor industry, where a balance between scale and security is crucial. They propose a design combining client-server and peer-to-peer models to address security concerns. The authors also examine common design considerations, including the use of space partitioning data structures, such as KD trees and quad trees, to improve scalability. They suggest evaluating the cost of infrastructure associated with storage solutions and understanding the trade-off between cost and security. A novel idea of creating a holdout reference set is proposed to add an extra layer of security, storing a finer representation of templates to refine authentication confidence. Signal processing techniques, such as suband decomposition, are also discussed to decompose templates into finer and coarser representations. The authors acknowledge the distinctiveness of their work, taking a holistic view of anti-counterfeiting systems, evaluating different prior works, and performing a systematic security analysis. The paper also explores the use of physical-unclonable functions, PUFs, in mobile cameras for counterfeit detection, highlighting the importance of authentication in supply chain management and the role of blockchain technology in enhancing security. Various methods for generating unique identifiers for products are reviewed, including using the microstructure of materials or laser surface authentication. The authors discuss the issue of spoofing attacks on biometric systems and the need for robust liveness detection mechanisms. The paper reviews different biometric systems and their vulnerabilities, highlighting the need for secure and reliable authentication mechanisms. The use of hill climbing algorithms in attacking biometric systems is also discussed, emphasizing the importance of developing robust countermeasures against these attacks. The authors emphasize the urgent need to develop robust solutions to combat counterfeits in the supply chain ecosystem, highlighting that different application scenarios require varying system designs. The concept of a decentralized, secure, and general transaction ledger, as introduced by Ethereum, is discussed, alongside Bitcoin's white paper, which introduced the concept of a decentralized digital currency. Efficient data retrieval methods are explored, including multi-dimensional binary search trees, KD trees, quad trees, and octrees, as well as hashing for similarity search in high dimensions. Blockchain data storage optimizations are surveyed, encompassing distributed file storage and access frameworks using IPFS and blockchain, consensus unit-based storage schemes, jigsaw-like data reduction approaches, and multi-level distributed caching for blockchain storage optimization. The authors also examine the concept of finite lifetime blocks with applications to edge-based IoT, decentralized data processing, and immutable storage for multimedia streaming. Multirate systems and filter banks are discussed, as well as scale space theory, distinctive image features from scale-invariant keypoints, and physical-unclonable functions, PUFs, in security protocols. The integration of blockchain into supply chains safeguarded by PU-enabled RFID is also explored. Key data structures and algorithms for efficient data retrieval are highlighted, including the use of hashing for similarity search in high dimensions. The Survey of Blockchain Data Storage Optimizations provides a comprehensive overview of existing approaches, including distributed file storage and access frameworks, consensus unit-based storage schemes, and multi-level distributed caching. The discussion of finite lifetime blocks and decentralized data processing highlights the potential applications of blockchain technology in edge-based IoT and multimedia streaming. The integration of blockchain with PU-enabled RFID in supply chain management demonstrates the potential for secure and decentralized data storage and processing.